So there are many types of these electromagnetic waves that Maxwell discovered, and you characterize them by their wavelength. So if we were to plot one versus position, the E field, it would be a sinusoidal vibration. If we were to plot it in time, it would be moving because it's a wave. And you know that the wavelength is usually called lambda, and it's just the characteristic repeat distance of the wave. So you can characterize them with a spectrum. Basically just plot them all versus wavelength and identify them. So we can start way down here. They tend to have, a lot of them have short wavelengths, 10 to the minus 12 meters, 10 to the minus 9 meters, 10 to the minus 6 meters, 10 to the minus 3 meters, 1 meter, 1,000 meters. Electromagnetic waves have been observed at this huge range of wavelengths. And that's why they seem very different. They behave very differently. If you are way at really short wavelengths, these are gamma rays that we see from space. Very high energy, if you think of them as particles. If you're between sort of a nanometer and to here, these are X-rays. You can think of X-rays as waves, very, very short wavelength waves. In this range, up to maybe a half of a 10 to the minus 6. This is called a micron, and this is a nanometer. So up to about 400 nanometers, this is ultraviolet. And between 400 and about 700 nanometers, this is light, the light that we know, the visible light. Light that is visible. If you keep going out to up to say a millimeter, this is infrared, also an electromagnetic wave. If you keep going out, you get into microwaves, and you get longer and longer, and you get into radio waves. But in terms of classical electromagnetism, they're all the same. It's really just a question of scale of the wavelength. We experience them different ways. So now if we zoom in on visible light, of course the colors we see are the wavelengths. So if we were to zoom in to here, 400 nanometers is violet, and then you have blue, and way out here at 700 nanometers is red, and it's Roy G. Biv, red, orange, yellow, green, blue, violet. You've heard that before probably. But this is all the colors that we see, and I forgot that at the very intro I said I was going to explain the double sunset of Tatooine. So let me do that real quick. Okay. Double sunset of Tatooine. Finally made a mistake. So in the iconic scene, we have Tatooine, and he's there, we're yearning to be in space, and you're looking at one sun that's kind of setting, and it's very red. And the other sun is out here, and it's sort of more yellow. And you wonder, did they get it physically correct, the two colors? And of course they did, because they were both shots of the sun, right? There were no special effects that could do that in the 70s. So it's probably some double exposed shot of a real sun going from red when it's low and yellow when it's higher. To understand this, you need to know why the sky is blue and about Rayleigh scattering. So small particles and molecules scatter light, and if we were to plot how much they scatter versus their wavelength, from 400 nanometers to 700 nanometers, from blue to red, it would go down very fast like that. So little particles and molecules scatter blue much more efficiently than they scatter red. Okay, so if you're sitting on your planet, and here's you, and you're looking at a sunset, you're looking at it through the atmosphere. So here's the atmosphere around your planet, and here's the sun out here. So if you look at the sun right when it's close to the horizon, it's really down here, you're looking through a lot of your atmosphere. And the atmosphere scatters out all the blue light. So the light is white when it leaves the star. We've evolved to consider it white, right? It's white when it leaves the star, and you lose a lot of the white, so the light directly that's white comes in. And if you lose a lot of the blue, you end up seeing something red. If the sun is a little bit higher, it still comes in, it's white, but it goes through less atmosphere. Less atmosphere means you lose less of the blue you have more of the blue left, therefore it's less red and it's getting more to include more of these wavelengths and including more oranges and yellows, so it looks dimmer. If you look at it right overhead, which is hard to do, it goes through the least atmosphere and that's when it looks the whitest. So that's why the double sunset had those two different colors. Another aspect of the spectrum I can tell you about is here. This is interesting, is infrared. That's basically heat. You can have sort of heat radiation. To prove that to you, imagine you're standing near a campfire. Right? There's a campfire. I don't camp much. There's a campfire. And here's you. And it's windy outside. If you stand near a campfire, it feels really hot. Of course, that's why you light a campfire. But say the wind is blowing this way. You might think it's hot because the campfire heats the air molecules, and those air molecules heat more air molecules, and you get conduction of the heat towards you. But that's not really what it is. Mostly, it's IR radiation. Hot things emit light. Okay? So this is actually electromagnetic waves hitting you. And you know that's true because you can also go downwind of the campfire. So if you go upwind or downwind, anywhere with respect to the wind, it may help you with the smoke, but the campfire still feels hot. Okay? When you're over here, the heat is not getting blown with the wind. It's not conduction through the air. It's actual radiation that's coming and hitting you. So all these different regions of the electromagnetic spectrum we understand, and they interact with us in different ways. So now, for our final demo, I'm going to prove to you that this IR radiation is heat.